Who wants to get that? Try to answer that.
I can give it a try. I won't be able to address all the questions. I can talk to when it fails. From my knowledge, and I'm not an expert on the statistics of bootstrapping, identifying when it fails is not necessarily an easy thing to do. But it's easy to say when it might fail. And for this, we should go back to the original idea of bootstrapping, which is what you want to do with bootstrapping is you want to simulate a new data set that you haven't collected. Now, clearly, if you only have a fixed data set, you can't do this. But the way that simulation works is you subsample from the data you have, and you treat this as if this were a new data set. And you do this over and over again and ask now for the new data set, what are the overall statistics across all of these possible data sets? Now, if your original data set is extremely small, let's say in the worst case, you'd have 2 examples, then just imagine how the subsampling would work. You would get, if you have 2 examples, you would either sample twice one, twice the other, or once the 2 of them. Right? And that already tells you, this doesn't give you a good idea of how the data in general would look like if you had more data. So in this case, bootstrapping would fail. It depends on how much data you have. For small data sets, bootstrapping might not be a good approach.
Yeah, I'd like to add maybe something that goes slightly in a different direction, but I think it might be interesting, is that you could also use bootstrapping to look at the sensitivity of your model with respect to the model parameters. So if you want your model to reproduce, some known phenomena, maybe you can use bootstrapping to say, okay, what is the range of parameters that allow me to actually reproduce that phenomena, and which range of parameters do not work. I mean, lots of people are using that in many, many different fields. I think it's important to mention that bootstrapping is used for many different applications. So if you go to health economics, where people try to, for instance, predict the cost of some treatment, they actually have different parameters with different ranges, and they use bootstrapping to sample from these possible ranges and see, okay, what's the distribution of cost that a treatment can have. So I think it's a technique that is really useful in many, many situations.
I just wanted to note maybe that it's normal that the bootstrap feels a little bit magical. Like, why does it work at all? And I love the story of the naming of the technique from this I think 1900s 1800s baron from Munchausen who was falling in some river or something, and he was told to pull himself up by his own bootstraps. So we know this should not work. It sounds crazy, and yet in most practical cases it does. And there is some beautiful math behind this bootstrapping methodology, and Brad Efron is the person who popularized it, and the book that he wrote contains a lot of this math. But the point is that in practice it works surprisingly well. It's like one of the big ideas of statistics in the last 100 years. It's something like, it's a major piece of contribution in statistics. And where it breaks is usually where you would expect it to break, when you're trying to build confidence intervals around some statistics that are statistics at the edge of your distribution, when you're trying to guess something about the maximum value. Of course, if you only have one sample and you resample from it, the maximum is never going to be more than the maximum of your specific sample. And so there are some of these issues that pop up. If your distribution happens to have moments that are not finite, like if you think of distributions that are not nice, some situation in real life have fractal behavior, like they don't have a well-defined variance, for example, then in this case, any statistic really is going to be in a bad place.
Does anyone want to comment about false positives and whether that's an issue in using bootstrapping?
So false positives, I'm not sure how to really interpret it, but let me say this. The idea of bootstrap is to obtain sort of a little distribution around the parameter to see how how trustworthy this particular inferred value is. So the outcome of this bootstrapping exercise is going to be a little histogram or something like this. So a false positive would be, I'm not sure how to interpret the false positive here.
Yeah, I mean, just continuing on your explanation, since you do get a distribution of parameters, you can essentially apply the same sort of statistical inference or reasoning techniques that you would traditionally use and ask whether that distribution is significantly different, for example, from 0, which is typically what you want to avoid false positives.
Yeah, so that's more with permutation test then, and where you compare. So it's basically the same. I mean, that's the number, the amount of false positives that you get in that case. You fix it by yourself by setting your own statistical threshold. I mean, that's very nicely described for all things linked to permutation tests.
Great. Next question is by Cédric Foucault. Today we talked about model complexity, but we did not formally define it. What are good practical ways to measure model complexity? In particular, for large models, such as neural networks, how should we compare their complexity? Is the number of parameters a fair measure, given that networks can have very different architectures with mechanisms that don't all change the number of parameters? So how do you define and measure model complexity?
So I can give it a start. I think the easy answer is that no, a number of parameters is not a fair measure of model complexity. It's the easy way to start. And I think it's reasonable to start there, but there is like old statistical wisdom that was passed along generation that said, you know, if you have less samples than number of parameters, you're going to be in trouble fitting it and you'll be overfitting to this small sample. And in practice, this does not always happen as we've been seeing in the last 10 years in the deep learning works. So there have been a lot of efforts defining new measures of complexity, and I don't think that any one of them really nails the whole thing. It's a pretty hard question. There are some works by the group of Neshabur and Srebro at Princeton University, and I think that they have like some path lengths. So it's hard to really pin down one metric that would be fair to all the models at once.
Does anyone else want to comment on that?
Yeah, I'm just going to add something very briefly. I think if you stick to linear models, number of parameters is a good measure for complexity. And this is actually most of these information criteria like AIC, BIC, and so on, usually have the implicit assumption that the model is close to linear. Once you move to nonlinear models, it becomes really hard, as Pierre-Etienne already said, to define complexity. One way to think about it intuitively, and that's also the way that Bayesian model comparison, for example, works, is imagine how many different data sets your model could generate. And the larger the number, the more complex your model. And if you, for example, that also means that if you turn this around, how much different data sets could you fit? If you have low model complexity, you can fit fewer data sets than if you've got high model complexity.
Great. The next question is by Alex. Coming from a machine learning environment and hearing that in neuroscience you use more the goodness of fit in comparison to train, testing, and validation, what would you say is the advantage besides being able to work with less data? And in your practice, which of the two has given you better results?
Well, I think you would use them for different purposes. If you're only interested in for instance, fitting some data that you have, then of course you're gonna look at the goodness of it. If you want to make some predictions about things, then you would more use a cross-validation approach or something like that. I think they have different purposes. I don't think one is better, or in practice, I don't even think that you can really compare the results of both approaches. I think that they have a different goal. If you want to predict something, use a cross-validation. If you want to fit something, then use the goodness of it to characterize. I think it relates to the fact that, the fact that when people do some regression, linear regression, they often say, yeah, variable X can predict parameter Y, but it's not. If you just fit a regression, you cannot predict anything.
Just adding to that, I think it was mentioned that coming from a machine learning background. So I see that in machine learning, train, test, split, or cross-validation is really the gold standard. That's how you've solved a task, that you are better at ImageNet than even an average human performance. I think that in our context, we might want to ask more of our models. So it's great to be able to have a good value on the test set, but ideally we would really want to be able to push our models further to see where they break and to draw inferences from them, to ask more than just having a good test accuracy, and see how can we synthesize then from this data and do a new experiment. So if the linear regression, comes out with a certain set of parameters, you can then evaluate your model in a part of the input space where you had not run an experiment previously, and then you have a prediction from your model, and then you can go ahead and run this experiment in the lab again. And hopefully that's where we start learning something with our models beyond just fitting them.
Awesome, thank you. Next question is by Jose Aguas Vivas. Beyond the bias variance trade-off, what other criteria can inform the model selection process? For example, model parsimony.
Well, I think a theory can also guide you, about selecting a model, depending on if you want to have a biologically relevant model that will also inform the model selection process. What could be implemented by the brain and what could not be implemented by the brain. That's also something that can guide you.
I think, yeah, that's theory, I think, is important, and biological realism, for example, if you actually want to model the brain. Another guiding principle might be if the model actually addresses the question you want to ask. Because you might be able to build models, but they don't tell you anything about the thing you actually want to ask. So that is also a very important guiding principle, as you've heard in day 1 and day 2.
Yeah, maybe I can remind everyone about this. Like when you want to set out to model something, you want to set out to get a deeper understanding of something, right? That is typically the goal of modeling at all. You want to get something out that you cannot just see from the data. Now, in order to do this correctly, as you learned yesterday, you need to essentially frame your questions correctly, right? You need to define exactly which phenomenon or which observation you want to understand. You need to ask a particular question, and you need to have like a particular goal in mind, right? What do you want to achieve at the end? And that essentially, that sort of framework will ultimately, together with your hypotheses that you might have or that the field might have about something, that will essentially constrain the model selection process. But if you do that sort of in a naive way, let's say, without looking too much at what's the favorite model that the certain field has been using or something like that, or that got the most citations, or that your supervisor tells you to use, or whatever it is. If you do that in that sort of like a blank mindset brainstorming way, then I think you can get rid of a lot of this prior preconception about what you should be doing in terms of modeling, and rather select the kind of model that suits your particular goals and your particular question. In that sense, as Jan says, if you do that, then you actually will get the model to answer, hopefully at least, if you do this correctly, answer your question and speak to the hypothesis and reach the goal that you set out to reach. That's a great question. Okay, next question is from Matej Znidarek. Is there some intuition behind the likelihood number or log likelihood that we computed in the maximum likelihood estimation? It's quite straightforward to think about mean squared errors and what they represent. Is there also some similar meaning or connection to the underlying data when we discuss likelihoods? It's a nice question. Who would like to give it a go? Jan, I feel like this is like a question right for you.
Okay, well, I can give it a try. I can give you the answer I already tried to promote in the intro, which is the likelihood comes from a distribution that is over your data. So it's the probability of your data given the parameters. And in that sense, this number tells you how likely is that particular data set for the chosen parameters. So that's a possible interpretation. One thing is that it's very dependent on how you choose the generative model. So the thing that actually defines this probability distribution. Because you could, for example, look at neural spike counts, and very often they are modeled by a Poisson distribution. That's fine because they're integer values and they're positive. So that is very suitable for a Poisson distribution. For other models, you might use a normal distribution. Now, the normal distribution is defined over all real values, positive or negative. That means that for a particular spike count data set, the probability of seeing particular integer values will be much smaller. So comparing those, for example, it's informative, but it's tricky to compare those across different models. It really depends on the aim you have when you're asking that question. I hope that was somehow clear.
Pierre-Etienne, it looked like you wanted to add something.
I really like what Jan just said, because it's like comparing the likelihood values of like several models, I think could easily be confusing. So if you just pick a model because it has a better likelihood value, like if you have a bigger model class, you're probably going to get a better likelihood value on your training data set. So there is something special with the maximum likelihood of a Gaussian model, because it falls back being mean squared error. So that's great. It's very comfortable. We're in a linear space, and it's projections and stuff we like. And what's great about the likelihood value is that it gives us a path toward defining these objective functions in other domains. So like Jan was saying, in the spiking domain where MSE would not make any sense, it gives us a way to get started. Like we can define a proper probability distribution and do 1 or 2 lines of algebra where we take the log and we do some independence assumptions. And here we get a good candidate objective function. Like finding good objective functions is really hard. Because there is always ways where it could go wrong, or it could like really maximize this objective but not do exactly what you intended. So it's a hard task for scientists to encode in an objective function what they really want their model to be doing. And having the likelihood principle and probability theory is really a great way to get a head start in that process.
So there's a related question that Oksana Zinchenko asked. While finding maximum likelihood estimators, we found out the equation we had to solve is the same for the optimal MSE estimator if noise is Gaussian. but what should we use if noise is not Gaussian?
So yeah, that speaks to what I was trying to express. So if the noise is not Gaussian, but you can have a model of this noise, nevertheless, you know that your noise is Poisson, for example, or that's what you're going to be working with for a start, then you can still do this this process of writing down what is the Poisson distribution, taking its log, and observing the form that you find. And it's not going to be terrible, okay? It's not going to be as simple as MSE, but it's going to be something that has a few terms, each of them interpretable, and will result in another objective function. Some of them will have names, you know, for other distributions, you'll end up on other familiar notions of distances. And then if you go a step up in abstraction and like, if you like that and think about exponential families, you can think of estimators like the maximum likelihood as projections in parameter spaces. And at the more mathematical level, some of these things can make sense again. But that's a different conversation. I think in practice, you want to be able to use the likelihood in the noise model you have to sort of build a good objective function.
Yeah. Okay, another question by Matteo Mancini. Can anyone of the speakers elaborate on the phenomenon, so this is in quote, the phenomenon and theory of double descent? It is mentioned in the bias variance trade-off notebook. I feel like Pierre-Etienne, that's almost a question for you.
Yeah, I can say a few words. Double descent is a new term that has become popular in the last few years to address this point of sometimes, even if the number of parameters is really large and you don't have that many samples, you can still have a good test error. And that's confusing because it's contrary to the old statistical wisdom. Okay, so that's the way it's often put. But actually, this phenomenon had been observed a long time ago in computational neuroscience work from the 90s. It's quite fascinating. It even works in linear regression cases. And there is now a fair amount of theory that's been done to explain why it is that you can get better test errors, even in the regime where you would normally expect to overfit. I think that this is a part that's of the theory of machine learning field that's very active currently, and people really are trying to find better measures of complexity, like an x-axis of this plot that's not number of parameters, where we do recover a bias variance trade-off. That's one of the things that are going on in theoretical machine learning these days.
Would anyone else like to add something to that?
I can probably just add an explanation, because I'm not sure if everyone knows what double descent is. And I'm not sure how much it was elaborated on in the notebook.
Yeah, that would be great.
So it's basically, if you recall, I had this in the intro, but you've also seen it in the tutorials. I had this plot where you have model error, model complexity. And the overall error was decreasing first because you decreased the bias of the model, and then it was increasing again. What I didn't show you is what's happening afterwards. So if you increase the complexity further, and it's been recently observed that some models basically decrease, then increase, and then they decrease again. And the second decrease is what's known as double descent. And that's particularly true for neural network models where you have many more parameters than actual data points. So the model complexity is extremely high in the number of parameter sense, but they still don't seem to overfit. And double descent is one observation that is trying to explain to some degree why this happens.
Great, thank you. Okay, the next question is by Marcel Jüngling. And Marcel asks, in the outro, it was indicated that the Bayesian framework is superior to the frequentist framework. Could you elaborate on why you think that's the case, and maybe also mention different opinions on that? That is a hot question. I feel like, Jean-Jacques, this is a question for you in a way. You have worked on this quite a bit.
Yeah, I mean, I don't know as much as of the Bayesian framework as I know from the frequentist one, but my impression is really that, you know, those are two tools that have different strengths and different weaknesses, and you need to use the right tool for the right problem. So there's not one that is superior to the other. It depends on what you want to achieve. And I think that's the best question. I mean, you can find tons of debates online between frequentist and Bayesian people. And I think at the end of the day, everybody sticks with his own opinion. But what I really think is that, you know, those are tools. Just use the right tool for the right problem.
Would anyone else like to add something to that? Any strong opinions?
Yeah, this is Konrad here. I know I'm not officially on the panel, but this is exactly right. You know, like what we just heard, that basically Bayesian and frequentist tools solve fundamentally different problems. And talking, and you know, like a lot of people hear about me as wearing my Bayesian hat. I'm sorry, I don't have hats because I wasn't prepared for today. But basically, this fight of those two against one another is pretty much over. Most statisticians I know like draw from both sides, and that's the right way of doing it.
And that's a very good point, I think, in terms of practicalities. It is often useful to report both the frequentist and the Bayesian statistics if the question calls for that.
Yeah, I'd also like to add that those are not necessarily completely opposite views, because there is actually a whole area of research where people are looking at frequentist properties of Bayesian approaches. So there is a bridge between those two things. It doesn't mean that you need to say you use one or the other. The problem very often with Bayesian approaches is that you have this very strong model perspective. You assume that there is a model that generated your data. And in reality, you always know that that model is wrong. But this is very often ignored in Bayesian approaches. And now a lot of people are actually looking at the question from the frequentist perspective and ask, if I now use the math that comes out of Bayesian approaches and ask what happens when the model is wrong, what are the consequences? So there is a bridge between those things.
Great. Thank you so much. Okay, next question is by Abin Krishnan. Why do people take a stochastic approach for modeling most of the time? Aren't there chaotic dynamics happening in the brain? Also, are there deterministic models in the brain that work really well? That's a very broad question. Who would like to give it a shot?
I can say a few words about deterministic or stochastic. I think that even deterministic models that we use in brain sciences can oftentimes be reinterpreted as having made some probabilistic assumptions. That's sort of the beauty of the probabilistic tools. They are ways to think about the problem, and you can often reinterpret a model as having made some probabilistic assumptions. So for example, if you fit logistic regression with MSE, you're really thinking of a Gaussian likelihood function, and making this explicit can help bridge the gap between stochastic and deterministic models. But in reality, in science, any measurements we make is going to be corrupted by some amount of noise, and wanting to take this uncertainty into account is really what makes the endeavor hold together. We want to be robust to these little imperfections in our measurement, and I think that most models are built to deal with that specific point. So that's about deterministic and stochastic models. But this is I think part of a longer process over centuries of science, where like reading the history of physics is fascinating. Like the learning to deal with stochastic models of the world was a hard step, and that was really done by statistical mechanics, and like understanding that probabilistic models can give a view of phenomena at a coarse scale is really interesting. It means that we can you know, take advantage of looking at the phenomena from further away and describe some of the noise that we see.
Jean-Jacques, you want to add something?
Yeah, I mean, at least in motor control, there are lots, and motor learning in general, there are lots of deterministic model, and it really depends on what you want to do. Do you want to model the average behavior, which is sometimes then you have enough with a deterministic model, or do you want to, you know, also look at the variability of the movements? In that case, you will need more stochastic approach, and I think both are fine. It depends again on what you want to achieve.
So why don't we have chaotic systems models of the brain? Or very few, at least. We have some. Why is that not more popular?
I mean, I can give you an opinion on this.
Yeah, absolutely.
People might disagree. But so if we assume that the brain is there to compute things, then chaotic dynamics might not be the best thing to do, because in computations you want to have predictability, and you lose that predictability with chaotic dynamics, particularly if you've got small element noise, which is what we have in the brain. Like the biological components are stochastic. If that stochasticity matters much, we don't really know, but at least for chaotic dynamics, it would matter a lot, because then predictability goes out of the window and that screws with your computations. So I think that might be one of the reasons, if people care about computations, that they don't build chaotic models.
I mean, it's not impossible to build chaotic models that do compute, but it's obviously much trickier, and it's not, that would be my point of view, it's not always clear what is gained from that in terms of insight. I think that is probably the most profoundly the deepest reason why there's not more chaotic models out there. It's very hard to gain understanding from them. Okay, that was it was a great question. Next one, another question by Francisco Sacadura. Why is the L2 norm most commonly used for model fitting? How does using other norms or the cost functions impact model fitting? How does norm order relate to the noise model assumed in maximum likelihood estimation? Who would like to give that a go?
I can give it a try. So a reason for L2 norm is because it's mathematically very nice. So it's just the easiest thing to do. You have these closed form expressions where you can plug in your data and you get your best parameters out immediately. Things become much more complicated once you use other norms or other error measures in general. The other thing is that, and this is something I'm not sure you're going to hear in the future, but you haven't heard until now, is if your aim is to best match the mean, so the average response, let's say, of a neuron or whatever you want to model, then the L2 norm is the adequate thing to use. There is a correspondence between the way you describe your predictions and the error you want to minimize. And for mean, it would be the L2 norm. So that makes it additionally appealing, because the average, the mean, is very often the thing you want to describe.
And to build on what Jan was just saying, there is a similar correspondence between the L1 norm, so just summing the absolute values of the entries in a vector, and this time the median. So if you have a few points on the real line and you ask what's the sum of their absolute values, and you want to find a number that minimizes the distance according to the sum of absolute values, the statistic that comes out is the median. And you can essentially rebuild a lot of statistics out of different measures of distance, like we just did for L2 and L1.
Yeah, great, thank you. Arash asks, the Kullback-Leibel divergence versus AIC metrics. Which one is better for generalization error estimation?
I think, even though I'm not 100% sure I understand the question, so let me phrase it the way I interpret it. So the question is, if you measure the KL divergence is a distance between probability distributions. So the way you could use this to measure generalization error is predict some data and then ask how different is it, let's say, from a test set. But I'm not exactly sure that this is the question. But if that's the case, KL divergence could be used for cross-validation. If you just apply it to the training set, you will get overfitting. So there is no penalization for model complexity, which you would have in the AIC metric. Whereas if you would use it for cross-validation to measure your cross-validation error, I think then it has the same benefits as any methods to use cross-validation. But maybe I misinterpreted the question.
Anyone want to add something to that? Okay, thank you. We still have time for a few more questions. So Sanket Patil asks, in today's tutorial, we inverted a matrix for the LSE estimator. What will happen if the matrix we use is a non-invertible matrix? And what will the alternative solution be in this case?
That's a great question. I could say a few words about it. So in the linear regression example we worked on today, it was built in a way that we knew the matrix was going to be invertible in a pretty robust way, so we didn't have to worry too much about that. But in practice, you would always need to think about this kind of issues, and least squares is often the way to go. So you can say, okay, my matrix is not invertible because it has eigenvalue that's 0. So these are terms that you will be more familiar with in 2 days if you don't already know about them. But you can still do a pseudo inverse operation, or you can add something to your matrix in order to make it invertible. So these are the two branches. And for this second branch, the idea of adding a little bit of the identity matrix on top of the matrix you want to invert in order to make sure that all its eigenvalues are above 0. This is directly interpretable in Bayesian terms and corresponds to having a prior in your model. So not only do you have a Gaussian likelihood function, but you also add a penalty or a prior on the norm of the parameters. And when writing the log likelihood function and taking its derivative, finding its maximum, setting it to 0, you will find that now the solution to this problem, which is called ridge regression, has an inverse of a matrix that's x transpose plus a little bit of the identity, and that's what making the problem invertible. So there is a direct link between the well-posedness of the inverse of this matrix and the Bayesian interpretation in terms of adding a prior, and it has a name, which is ridge regression.
Anyone want to add something to that? Someone in the comments, Giuseppe Marazzo, mentioned that you can also use singular value decomposition.
Sure.
To get around that.
So that would be, yeah, Jan.
I mean, the general reason why you would find a non-invertible matrix is because your problem is ill-constrained. So you have multiple possible solutions that explain your data equally well. Pierre-Etienne has already mentioned you could use the pseudo-inverse, and one property of the pseudo-inverse is that you find one specific solution, and it is the solution that has the smallest coefficients. So if you have that problem, you could either go for ridge regression, or you can just say, I don't really want to artificially define an additional parameter to squash my parameters, but rather I just go for one solution. And for this, you could use zeta inverse, which gives you the one with the smallest parameters in the least square sense.
Great. Yatin Azad asks, can we please have a discussion on AIC and what is the implication of having negative AIC for certain polynomial orders? Who would like to take that?
I'm kind of shying away from the AIC questions because that's not a method I use much. The reason being that the assumptions that are made by these methods are things that I usually cannot verify in practice for the problems I work on. So although it's very useful, in the models I've encountered, it was not the best tool. So I can't really say that everyone always uses AIC because oftentimes cross-validation is a practical thing that can give you what you need.
Okay. Yeah, there was a related question by Arash, actually. Is there a meaning to negative AIC values? What does it mean? Or is that just a numerical sort of glitch?
I can't answer properly this question. We will need to backtrack, the exact equation and then work it out on the board. It's not a glitch. It's what the method is doing given the assumptions that are embedded in it, and it's not always the most practical tool.
Yeah, I think probably overinterpreting the exact AIC values might not be useful. What's most useful about AIC is to compare it across different models, and that's its main purpose, I think.
Yeah. Great, thank you. Roberto Mafuli asks, I'm not sure I understood entirely the difference in the meaning of the confidence interval between the maximum likelihood estimation and Bayesian framework as explained in the outro video.
What does the outro video say? It's difficult to answer without knowing what is said in the video. So
yeah, so I mean, someone comments on this. Rishika Mohanta comments and says essentially the difference between the two is that one is derived from the frequentist framework, the other one is derived from the Bayesian framework. And so as such, one is sort of like data driven, whereas the other one includes some prior information potentially. I think that would probably be the answer to that question. I think we should actually start wrapping it up. We've been, despite our delay, we have been doing this for about an hour, and the students, I think, should, and also our TAs could use a little bit of a break before they have to do project works. So again, my apologies that we had some technical glitches. That was kind of out of our control. And also, if we didn't get a chance to answer your question, please do copy it over into the Neurostars forum to have a discussion there. I'm sure that lots of questions that you have can be answered by your colleagues or by some of us that will be on the forum. And with that, I'd like to thank Jan Drugowitsch, Jean-Jacques Orban de Xivry, and Pierre-Etienne Fiquet again for sharing their insights with us. And see you soon. Thank you so much.
Bye-bye.
Hey, everyone. Bye.
Bye.